All right, back from break. Let's look at some examples of vibrational quantum state energies in diatomic molecules. Now it looks like what they're giving us is the hydrogen molecule. So let's see what they've told us. When the hydrogen molecule absorbs or emits photons, they're saying it's in the infrared part of the spectrum, and so it's higher energy than the rotational transitions, and it's at 2,300 nanometers. So what they're doing is say use this information to map out the energies of the quantum states. So let's do this. Here is state number 1, the excited state, down to state number 0, and this is our formula for the vibrational energies. And so state number 0, now this is interesting. In terms of vibrational energy, you can't have 0. There's always some vibrational energy present. I don't know if you guys remember the movie, the original Incredibles. It was one of the Pixar really popular movies. The kid in that show who became the powerful, really powerful super villain, I guess, had harnessed what's called the 0-point energy, and that's it. So what we say is that there is a 0-point energy, even if these molecules of hydrogen were brought to absolute 0, right? At absolute 0, they would still have vibrational energy. There is no such thing as taking all the energy out. There is only bringing everything into the ground state. So absolute 0 now means bringing all of the molecules, all of the systems into the ground state energy. That's the lowest possible energy we could have. So let's see what information we've got here. Let's get the reduced mass figured out. So this is the mass of hydrogen. Now I overdid this. I always become a little obsessive with hydrogen because it's 1.00. At that point I'm thinking I'll just use 1, but then I see the next number is 7, and ooh, and there's an 8. Maybe I need to put an 8 here, which would round to a 1. So I just put extra ones in. So the reduced mass then, using the reduced mass formula, works out to be 8.37, 10 to the minus 28 kilograms. So I've gone from atomic mass units to a reduced mass in kilograms. So I'm done using this formula. This is just a little reminder here that I'm getting a certain amount of amplitude of vibration taking place, and then there's a bond length present. Now what they told us was that the transition between vibrational state is radiating photons or absorbing photons with a wavelength of 2,300 nanometers. That's the characteristic wavelength for the vibrational spectrum of an H2 molecule. And so that says that the spacing then between these states is 0.539. Now the energy of the lowest possible state is 1/2 h bar omega, where h bar omega is the energy of the photon. So that lowest state is 1/2 energy of the photon. The excited state is 3/2 the energy of the photon. I can figure out how much vibrational energy there is at the lowest possible quantum state, and then I can find out how much vibrational energy there is in the first excited state. So let's do this. They want us to, I want to, go in and calculate K. Did they ask us to do this? So here's the bond stiffness. It's given by the reduced mass times the frequency. Now the reduced mass, we calculated up here. The omega is going to come by taking the energy of the photon and dividing by h bar. And that gives us 8.17, 10 to the 14th radians per second. The nice thing about being in radians is we can drop it when we don't need it anymore. Radians are unitless. And so the K value calculated from here, everything's in standard units, 5.59 newtons per meter. That is how stiff the H2 bond is in an H2 molecule. Now what that's saying is it's giving an idea of as the nuclei shift back and forth inside the electron distribution, how stiff is that? Is Is it kind of floppy where, you know, the two nuclei can move back and forth easily quite a bit? Or are they constrained by the surrounding electron distribution? And that's, you know, that's not a terribly low number. It's not a terribly high number. So it's kind of an average value of a bond stiffness of 559 newtons per meter. What's interesting is the bond stiffness we get for chemical bonds, it's kind of the same order of magnitude as an everyday spring. A moderately stiff spring that we might pick up is the same K value as chemical bonds. All right. Now, in terms of molecular spectra, so what's happening here is that we've got a lot of stuff going on. We've got the electron states, we've got the vibrational states, we've got the rotational states. How could we represent those? Well, let's say that we have a 3p electron state, and within that are a couple of rotational states, and then within the rotational states are the vibrational. So when you're working with these quantum states, you can't completely isolate the rotation, vibration, and electron energies, because all three could be happening at the same time. You could have an electron that's dropping to a different quantum state, and at the same time the rotational and vibrational states are affected. So, and they're just showing this as an example, that spectra are more complicated. So what you end up with are these spectra. This one is for hydrogen chloride molecules, not the solution hydrogen chloride, but molecules, vapor hydrogen chloride molecules, and looking at the spectrum. And because of rotational and vibrational effects taking place at the same time, there's a range of energies where we see peaks. And that has to do with this effect. It has to do that the molecules are transitioning from a particular vibrational and rotational state into a different vibrational and a different rotational state. And that means that there's more options than just one. And so you're going to get several lines instead of just one. All right, let's move on into kind of the second part of the chapter, and that is looking at solids. So first of all, we looked at molecules, chemical bonds, rotational and vibrational energies. Now we're going to look at solids. Solids, in some sense, are a little more complicated. We've got a lot of stuff going on. We've got many atoms interacting with each other. Here is a block of sodium chloride showing what the configuration looks like between the sodium and the chlorine molecules. Here it's saying that metal bonding tends not to be as strong as ionic or covalent, but they're still strong bonds. Now, in metals, so what we want to do now is start thinking not so much as sodium chloride, but let's spend some time. That was a really quick coverage of crystals. We did one slide. Yeah, basically. Now we're going to move on and take a look at electrons in metals. And this is kind of the bulk of what we see for this later portion of the chapter. And again, as always, let the homework problems be your guide. Look at what homework problems are assigned. Those are the ones that will represent the level of difficulty of problems that you want to be able to solve for the course. That's what the course is pitched towards. In metals, when we look at the electron wave functions, we find that some of the electrons' wave functions are spread out over large regions of the metal. We're often thinking that electrons are assigned, this electron's assigned to this nucleus and this electron's assigned to this one, and that's just not true. What happens in metals are an extreme example of this, is that an individual electron could be spread out over a wide range of nuclei. So what we do is to represent that, we say that this is called the free electron theory of metals, The idea is that every electron kind of is spread out over the entire piece of metal, and by making that assumption, what we're going to find, we'll see this in some future slides, here is a formula that tells us something about what's called the density of states. So when we take a block of metal and we start placing electrons in there, the electrons end up feeling the effects of the entire block of metal plus all the other electrons. And so there's kind of an average effect that each electron feels. We can show quantum mechanically, so here's an example of this applied to a block of copper. So copper is a very good electrical conductor. If we go back to chapter 39, I guess, and look at the electron configuration in copper, it's 1s2, 2s2, 2p6, 2, 3s2, 3p6. Those are core electrons. So of copper, copper is element 29, and 18 of those are well established as core electrons. They're attached to one nucleus. But that last row in the periodic table, that last row of electrons, the 3d10 and the 4s1, particularly the 4s1, this is like a valence shell, which means that electron is available to form chemical bonds with other atoms. Now, for metals, which are the majority of elements in the periodic table, most elements fall under the category of metals. Instead of 2 coming together or 3 coming together or 4 atoms, we can have any number, right? You know that you can melt down a piece of metal and reform it, and that new piece of metal could have any number of atoms, and they stick to each other. So what has happened is, here's our block of copper. Each atom of copper we can think of, we're doing some bookkeeping now, each atom has a bunch of core electrons. So we're going to treat these top ones as definitely core, and these as, probable core electrons too. So we're really coming into these 4s electrons, and each atom brings with it one 4s electron. So if I have n atoms, that's going to provide n free electrons. So if I have a block made up of n copper atoms, there are n electrons holding it together. And those electrons, instead of being assigned to individual atoms, are allowed to spread out through the entire block of copper. Now, along with the n free electrons, they are bringing in 2s quantum states. 2n 4s quantum states. So they're bringing in some quantum states too. Now this is kind of a mathematical thing that says that the number of quantum states that we bring in, so we're bringing in 2n quantum states, those quantum states are shapeshifters. Those quantum states can be mathematically reconfigured into a set of quantum states that look different. So the 4s quantum states within individual copper atoms, well, those were spherically symmetric. Those can all be mathematically combined into quantum states that spread out over the entire block. When we do that, what we find is that the 4s quantum states now show up as a band. By band, we mean that there's an energy associated with this quantum state. There's a certain potential energy of this band, and then there's a certain kinetic energy of the individual electrons. And so these 4s electrons are going to form a 4s band. Now, this band of quantum states, there's going to be really, really small spacing between the quantum states. So the quantum states are not going to be identical in energy. There's going to be slight differences between them. And in addition to the 4s band, what we're going to do is go through and imagine also what can happen is the 3d electrons can form a 3d band. So all of these states, the 3d states that all of the copper atoms bring with them, those can be mathematically reconfigured into a set of quantum states for all of the 3d10 electrons, or the 3d electrons. Now, there's enough electrons coming in from the 3d states that this band is completely filled. There's no vacancies, all the states are filled, electrons are not able to move around. But in the 4s band, only half of the states are filled, because each copper atom brought in only one electron, but they brought in 2 quantum states. So that says that there's going to be a bunch of states here that are filled with electrons, but there's going to be an additional number of states that are vacant. And because these are so closely spaced, electrons that are near the top of those electron-filled states are going to be able to move into other states. And electrons moving from one state to the next, that's electrical conduction. So if electrons are able to move from one quantum state to the next, that's the equivalent of electrons moving through that material. And that's why metals are good conductors. What they have are quantum states, series of quantum states where the states are very closely packed in energy. And that there's a boundary called the Fermi energy, where below that boundary the states are filled, but above the boundary there are going to be vacancies that the electrons can temporarily jump into. So electrons can jump back and forth above the Fermi energy and back down below and above and below, and that allows them to make their way through the piece of copper. Now, on that previous slide, there was this formula talking about the density of states. I'm not so, we'll come back and maybe look at some examples of this. What this is referring to is when these bands of quantum states form for the 3d electrons or for the 4s electrons, there's a certain spacing between them, and the density of states have to do with how closely packed the quantum states are in terms of their energy. Okay, this is a derivation of that formula, and you guys, I'm going to go through this quick. This is certainly not required, but what we do is, if you remember back in chapter 38, we looked at a three-dimensional example of quantum states for an infinitely deep potential well. Well, this block of copper sounds like a good utilization of those quantum states that we had identified. So what we could do is, we could, for the time being, we could imagine a block of copper that's shaped like a cube. Now, of course, we don't, the results we end up with are not going to depend crucially on the shape of the copper. So we're going to take some block of copper, let's say cube shape. We've already looked at the quantum states. They were a bunch of sine functions multiplied together, and these were the energies that we calculated. We had determined that the lowest energy quantum states came from quantum numbers 111. And then 112, 121, 211. So we had gone through and imagined all of the possible combinations of 3 integer values, and each one would give us a quantum state. Well, that's the equivalent of bringing out a coordinate system of nx, ny, and nz, and placing a bunch of unit cubes. Now, these cubes are just mathematical. They're not related to the copper cube over here. This is a way of keeping track of all the combinations of nx, ny, and nz. What we're going to do is combine those as if they were components of something called just n squared, where the energy of the nth state is given by this formula. And then, and again, we're going to count the number of states. So by calculating the volume, which would be 1/8 of a sphere in terms of little n, what we can do is we can get a formula where the little n in our formula can be replaced by big N, where n is simply counted 1, 2, 3, 4, 5. So what we've done with this calculation over here, and if you want to see the details, stop by office hours, we've gone from a bunch of states like this that required following and making up a pattern of 3 quantum numbers, and we've replaced it with simple counting, 1, 2, 3, 4, 5. Now, the downside on this is the formula we have is not exactly giving us the energy of each state, but, you know, the response to that is, doesn't matter. It's giving us a very effective way to count the states, and it's giving us a reasonably good approximation as to how the energies will compare. So this says that, ooh, and I don't think we're quite there yet, right? Okay, and I think what happened here, oh, I see. Yeah, this is a problem. So, and the textbook follows the same notation. So what I've done, what's happened here, is we've used little n to represent the sum of these quantum numbers, but then once we get through that and replace it with big N, then big N gets brought in and combined with the volume to become number of electrons per volume. I apologize for that. That's really, I should have picked something different here. But the little n now in this formula, let's go back to this one. So the energy of the nth quantum state is given by these constants times whichever state we're looking at numerically, just being counted 1, 2, 3, 4, 5, and then multiplied by Planck's constant, the mass of the electron, and the volume of the piece of metal. So let's see how this would work. Here is copper. So if I take a block of copper and I want to find out how many electrons there are per volume in a block of copper, I could start by or how many atoms. I could take the density of copper, 8.96 grams per cubic centimeter, multiply that by the molar mass, and then do some units conversions. And then what I've done is I've used Avogadro's number to convert the moles into atoms. The combination of density, molar mass, units conversion, and Avogadro's number leaves us with copper has 85.0 atoms per cubic nanometer. Okay, and I kind of like the cubic nanometer because it's small enough that it's a number of atoms that I can imagine. I can imagine 85 atoms. So every cubic centimeter of copper, or cubic, not centimeter, but nanometer, has 85 atoms in it. Now what we can do then is we can take that number and use that to calculate the Fermi energy. If you remember, the Fermi energy had to do with the energy at which we have run out of electrons. So it's the boundary between where the states are filled and where they're no longer filled. And so I can put in those values for n over v, which I like better, n over v here, and it says that the Fermi energy is 7.06 eV. So what that says is, in the 4s band of states within copper, there's going to be n of those states that are filled, where n is the number of atoms, n of those states that are vacant, a total of 2n, and using this formula we've shown that the Fermi energy comes in at 7.06, and the energy at the top of the band is at 11.21 eV. Okay, and that's kind of extreme. I think there's some homework problems possibly where you are calculating a Fermi energy. The density of states comes from taking this formula and inverting it. So what we do is we take our energy formula that we have and solve it for n and take a derivative. What that leaves us with So the density of states is defined as the number of states per energy interval. And when we do that, we get a formula for the density of states. It says that if we start at the low end of the band of quantum states, if we start at the low end of the band of quantum states, that as we move through the band, the states are actually packed closer and closer. There are more and more states as we move through the band. Once we have finished through half of the states, we will reach the Fermi energy. Once we are through the entire band, we'll be at the maximum energy. And I'm not even sure. Take a look and see. There may be a homework problem where you plug in some numbers, but I don't think it's going to be much beyond that. Okay, so what we can do then is we can work from the formulas that we've developed here. So this is the energy of the nth state in the block of copper. This is the quantum number for a given energy. So we've taken the formula, we've written it both ways. It can either be, if they tell us which state we're looking at, we can tell them what energy that state will have. If they tell us what energy we're looking at, we can tell them what number, counting from the bottom up, which n value we will have for that particular state. So here we go, a 1 cubic centimeter piece of copper, and we're going to count some states. So it says, if we take 1 cubic centimeter and plug into that formula for an energy of 5 eV, we find that we have to count through 50.7 times 10 to the 21 states. If I put in 5.5 eV and redo that calculation, I now have reached the state 58.6. Now remember, the Fermi energy in copper was at 7 eV. So the states I'm looking at in my block of copper definitely have electrons in them. There's plenty of electrons to reach up to 5 eV. There's plenty of electrons to reach up to 5.5. Once I get up around 7 eV, I'm not sure if those states are filled. So subtracting these numbers will tell me how many states and how many electrons in that block of copper within the 4s band will have energies between 5 and 5.5 eV. These are going to be filled with electrons. Taking the difference between this, it's 7.9 times 10 to the 20. I did everything in terms of 10 to the 21. I did the subtraction so you could kind of see what this is saying. Now, this becomes important in designing different materials. You know, so many, and this is another example with calculating a Fermi energy. But so many of our materials today that we use in semiconductors, you know, there's a computer chip inside my MacBook, and it's got, I don't know, 100 million transistors or something, and it's all done with very, very thin layering of different materials and understanding how the different quantum states are going to be arranged within those materials. So just as a follow-up with this Fermi energy, what's going to happen is, with our block of copper, this is representing how many states we've got, and the states are going to be filled right up to the Fermi energy, and then nothing's filled if we're at absolute zero. So if we're at absolute zero, the electrons have dropped to the lowest available states. Now, if the temperature is a little higher, then what we can show is that some of the electrons that were in states below the Fermi energy are able to appear in states beyond the Fermi energy. So this provides a very short gap between states, and electrons can easily move back and forth. This is an extra factor. This G sub E is the density of states. That gets multiplied by the probability that a state is occupied. So this is the probability of having an electron in a given state. If we put in the energies and put in the temperatures, we can calculate the probability. So again, the band theory of solids says that we start off with a bunch of atoms, and then we combine those into molecules. When we do that with metals, there are many atoms that are being joined together, and the allowed energies end up creating bands. So there are these regions where there are quantum states available for the electrons. A good conductor in the highest band, this band is filled, but this one has vacancies within the band. That's going to be a good conductor. Very easy for electrons to move back and forth between the states in the 3s band. Now, this is a good conductor. I'm looking within the valence band, and there are vacancies present. This is an insulator. The valence band is filled. There's a large gap until we get to the next band. So the conduction band for an insulator requires the electron to jump by a significant amount of energy. Here the electrons pretty much needed almost no energy at all to move into the unoccupied states. Here they need a lot. Now a semiconductor still requires electrons to move from a valence band into a conduction band, but the gap is very small. So materials like silicon have relatively narrow gaps. Again, this is the probability function showing how likely, I don't think I'm going to bother with this example. You can plug numbers in. This is in, the example's in the textbook, so you could take a look at that and just play around with the numbers here. What they're looking at are energies, to see what it would take, how likely it would be to have an electron jump the gap. So I'm going to say don't worry about it unless you're really interested in plugging numbers in. Again, I think I'm not going to worry about this. I want to move on to the semiconductors and really just talk about semiconductors conceptually and have a little background in what these semiconductors' properties are. So with semiconductors, we typically start off with silicon or germanium as a starting material. And they already have fairly short energy gaps between the electron quantum states that we're looking at. A tiny amount of impurity actually creates intermediate quantum states. So let's take a look at a diagram and see how that works. So first of all, here are the silicon atoms, and here are electrons that are arranged around them. I don't think that's very instructive, other than let's put in an arsenic atom. Now an arsenic atom can be substituted in where it maintains the same crystal structure, but what we've got at the location of the arsenic atom is an additional proton in that nucleus, and there's an additional electron. Where is that electron going to go? Is it going to fit into one of the existing bands, maybe the lower conduction band, or valence band, or maybe a higher valence band? The other option would be, let's pick something in the column of elements such as gallium, which has 3 electrons instead of 4 in the valence electrons. And that means when the gallium gets substituted into the crystal structure, there is an opening for an electron. These are referred to as holes, or a spot where an electron is missing. So these materials are called being doped. We're putting little bits of electron providers, electron donors, and electron acceptor materials. Okay, so it creates an opening for the electrons. So this is what happens with the band structure. If we put in something like arsenic, which has additional quantum states, those quantum states end up filling, or not filling, but appearing with intermediate energies. They're not part of the valence band, but they're actually similar to the conduction band. So what happens with these is that the arsenics bring in additional electrons, there they are, and they bring in additional states and electrons to fill them. And so here are the electron states, and the electrons that are filling them can easily move into the conduction band. So by putting a little bit of a type 5 element, column 5 I guess in the periodic table, compared with silicon, which is in column 4, we've got that extra state and an extra electron, and we can have those electrons now become conducting. If I put in something from column 3 in the periodic table, that creates vacancies within the valence band, and it also creates states that are in the intermediate region. And so what can happen here is, now that we have these intermediate states, electrons from the valence band can jump into these states. So what happens is, we've created a set of quantum states for the electrons in that energy gap region. Okay, so let's try operating this. What we'll do is we'll take some p-type material that has the missing electrons with the n-type material that has the extra states and the extra electrons, attach that to a battery, and what can happen is the electrons can flow. This is the n-type material, and electrons coming in, pushed in through the battery, are coming in through this intermediate state at a higher energy level, and they can be pulled into the lower intermediate set of quantum states. So if I use a layer of n-type material, n for negative because I've got more electrons, but I also have more quantum states. The material itself is not necessarily negatively charged. And then a p-type material, p for positive, I can have electrons drop from these n-type intermediate states into the p-type intermediate states. But it doesn't work in the reverse direction. And so what happens is this: when we reverse the direction of the electrons and push electrons into here, well, this is still quite a gap. And so the electrons are not easily able to move from the acceptor levels into the donor levels. And as a result, a device built out of two layers, one of each of these types of material, favors one direction of current over another. So if I am, now this is the direction of current flow, but for this setup, I want to talk about electron direction. Electrons are being pushed this direction. They're being pulled through the battery here. So I've got electrons here. They show up as a surplus in the n-type material, drop into the lower p intermediate states, and continue on their way. On this side, the electrons come in through the lower states, and there's still an energy gap, and they're unable to bridge that gap. So it prevents the current from flowing. So very clever devices, these are called diodes. If we pattern these, again, what's happening in the NP type diodes is electrons are being pushed through these higher energy states. They're able to drop into lower states. And so as the voltage goes up, the current begins to rise not linearly, but exponentially. Now what happens if, and this is the properties of a diode. So for a diode, if we push the voltage in what's considered the forward bias direction, what happens is we do see a sharp increase in current. But if we try and push current in the opposite direction, we have to push really, really hard. Notice here, by the time we got to 0.6 volts, 0.8 volts, we're getting a lot of current. Here, the graph is showing that we've reached 12 volts in the opposite direction before we're able to overcome that gap. So in one direction there's a gap that allows us, the electrons to drop, which is easy enough. In the opposite direction it requires the electrons to climb through an energy gap, and that requires a much higher voltage. Okay, so again, I'm not going to worry about the example that I have here. In fact, maybe I'll remove some of these from the examples. So a diode can actually be used also as what's called a rectifier. It can change alternating current into DC, because what happens is if I get a series of diodes set up, what initially was coming in as an alternating voltage or an alternating current ends up generating an intermittent current in just one direction. That can be connected to a capacitor. In this case, I guess we have actually a resistor between them. And it can be smoothed out. So diodes are very useful for converting AC to DC. And that's an example of this. Now, what would happen if we took 3 layers of this material? So let's take an N layer, a P layer, and another N layer. Or alternately, we could do it the other way around, but I think it's easier to think in terms of NPN, because that allows us to follow the flow of the electrons. Going to PNP is likely to be a little more confusing. But an NPN transistor, so this is what a transistor consists of, is 3 layers. And for the transistor, what we're going to be doing is we'll start out, let's say, with a layer of N-type material, followed by some P-type material, followed by another layer of N. Now, when I drive current into the transistor, the electrons are filling these states within the gap. When we get to this thin layer, this base on the transistor serves as kind of a switch gate. Depending on how thick this layer is, some portion of the electron, some fraction, will drop into the lower state and then be drawn away through a wire that's attached to the P-type material. But alternatively, we could have the electrons tunnel through the intermediate layer. Those electrons could cross through the gap, through the P-type material into the N-type material on the other side. And that's why transistors are often referred to as switches. So there's 2 possible directions that the current could flow, and what it's going to depend on is the thickness of the intermediate layer and the placement of these different quantum states and their availability for electrons. So if we go back and we look at the circuits here, so let me go back. Ooh, maybe we don't have it. Oh, here's a good one. So let's say that we have a circuit here. Now, let's not think of the arrows so much. Let's look at the batteries. So I've got electrons. This battery is providing electrons in this direction. And here are the electrons coming into the transistor. So the symbol here says the electrons come in. They can either go out through the base, or they can continue on into the other part through the collector of the transistor. So the emitter, the electrons are coming in. They can come out through the base or through the collector. And so this part of the circuit is driven by a voltage source, and this part of the circuit, now this is probably an amplifier circuit, and so these transistors can be designed so that the portion of current coming through these 2 directions is proportional to the signal that's coming in through the the signal that's coming in through the base. So whatever we have, the signal that's showing up at the base will control what goes out through the collector, and we can use our voltage sources to create a scaled up current pattern. So we can take a signal that's coming in through the transistor and we can create a larger signal coming through the other portions of the transistor. Okay, I think, yeah, this is a good place to end the chapter. So I think our emphasis with this chapter, certainly more so on the early part of the chapters, looking at chemical bonds, looking at rotational and vibrational energy states of diatomic molecules. So we looked at those in a fair amount of detail. So take a look at those. I think there's a good number of homework problems for those. And then as far as the later part of the chapter, we do have some of these problems that deal with kind of a conceptual understanding of these bands and how they get set up inside metals. So some of these examples with copper, going in and counting how many states we have within the copper, how many electrons we have within the states. Okay, so looking at the free electron theory or model for metals. So again, any kind of questions that come up, stop by office hours. Again, take a look at the homework problems and then come in with whatever questions that you've got or any of the stuff that we've talked about in lecture.